Steam-assisted gravity drainage systems, or SAGD, are a vital piece of Alberta's energy sector and the subject of other future energy systems project. SAGD wells go deep underground, with one injecting steam into the oil reservoir to reduce its viscosity, while the other collects oil and pumps it to the surface. Reliable, robust sensors are required for real-time monitoring of factors such as blockages, corrosion, pressure, and temperature, each of which can impact productivity and environmental safety. Our project focuses on producing a temperature sensor which can operate as a standalone device or as an integrable component for temperature calibration of other sensors. Not only does the sensor have to detect temperature change, the materials of which it is comprised must be suitable for harsh environmental conditions, specifically temperatures of up to 250 degrees Celsius. Our temperature sensor has the advantages of low cost, low power, versatility, manufacturing ease, and simple design. The exterior of the sensor consists of two thin sheets of copper, which are bonded to the surface of the substrate layer beneath each. These sheets offer the sensor innate protection from its surroundings. No factor other than temperature will impact the sensing, and it will be less susceptible to oxidation. We call these ground planes. The next layer of the sensor is the substrate, also known as dielectric. This is a non-metallic solid with important electrical and mechanical characteristics. We chose a dielectric that was electrically sensitive to changes in temperature and robust. Finally, encased in the dielectric, there is a thin copper pattern. The longer lines, called transmission lines, allow for power and communication in and out of the sensor. The ring interacting with the surrounding dielectric and ground planes give the sensor a signature. The peak of this signature profile is called the resonant frequency of the sensor and is what we use as a reference. A temperature change creates a measurable shift in the resonant frequency. Being encased in dielectric and shielded by ground planes, electric fields produced at the ring are completely contained within the dielectric. When there is a change in temperature, electrical properties of the dielectric change, subjecting the fields which pass through it. This phenomenon is what causes the shift in sensor resonant frequency. As temperature increases over a given range, so does the resonant frequency. By focusing on the resonant frequency rather than the entire signature profile, we can determine the sensitivity of the sensor from the slope of the plotted resonant frequency versus temperature data. The sensitivity gives us information about the amount of resonant frequency shift per degrees Celsius of temperature change. Future improvements to the sensor's design include metallizing the edges and applying protective coatings. We will also explore the use of advanced materials and geometries to improve sensor lifetime and detect smaller variations in temperature. Thank you for your time and attention.